Thank you everyone for attending my PhD defense. My PhD defense topic is knowledge-intensive natural language generation. Let's get started. Knowledge-intensive natural language generation, shortened as KINOG, automatically retrieves and processes data, and then generates the text with a focus on domain-specific knowledge. KINOG is important regardless of whether the mainstream foundation models are earlier small language models or latest large language models. And this dissertation interviews two parallel lines of research in KINOG. They are related work generation, which is a very specialized problem, and more established KINOG tasks, such as dialogue generation, question answering, and claim verification. So here's the overview of my topic to cover. First, I will briefly give some background on the related work generation task. And then the next two sections will cover the two datasets I built, one for related work generation and one for dialogue generation. Next, I will apply CORWA and retrieval augment generation for citation text generation. We dive into the mechanism of RAG and investigate the optimal form of RAG inputs. Lastly, I will show the application of LLMs for domain-specific tasks, such as related work generation. I'm going to be brief about the CORWA project, MISWA project, and the cited text span project, and also skip the wizard of shopping in the interest of time, since I have already presented once during the proposal meeting. Okay, let's start with related work generation. So imagine you are writing a paper and you already finished everything in the paper except the related work section, so that you can use everything else, such as the other sections in the target paper and the full text of a list of the cited paper to generate the related work section. So my first project creates resources, including the dataset, task, and the model for my subsequent projects. Previously, all the related work generation works all use the sentences as the basic unit for extractive and abstractive related work generation. However, obviously, this is an oversimplification of the problem. Intuitively, there are long citations that contain a few sentences, such as the citations in line 6 to 8. It contains two sub-sentences. And there are also short citations, such as pointer generator network here. There are only just a few tokens. Inspired by these observations, the CORWA paper creates a dataset to annotate the following labels so that we can use them for related work generation. They are discourse tagging, citation type recognition, and the citation span detection. Discourse tagging performs the sentence level sequence labeling. For example, we distinguish summarization style sentences and narrative style sentences. As for the citation types, we distinguish two types of citations, dominant type citations and reference type citations. Dominant type citations are usually long, while reference type citations are short citations that I've shown before. Citation spans refer to the text span that is derived from the cited paper, and they are the natural range of the spans than the sentences. This is an implementation of the transformer-based tagger model that we built. We trained jointly on all three labeling tasks. So overall, this project builds a foundation for later projects, and I will refer back to this project later. Next, let's talk about another important foundation of this dissertation. So before I introduce the next project, let me give you some preliminary. First, retrieval augmented generation, shortened as RAG. RAG refers to generating the text based on the retrieved text that the generator may have not seen before. The benefit of using RAG is that we can keep the model output up to date even after the model is trained. And therefore, the model does not have to memorize everything. And this makes it easy to adapt the model to domain-specific tasks, such as adapting GPT-4 for real-world generation that I will introduce later. Note that RAG works both for early small language models and also large language models. And in general, there are 3 steps involved in RAG. First, we need to use retriever model to retrieve the documents. And then optionally, we perform a selection step by re-ranking the retrieved documents. And third, we feed all the re-ranked documents and also some other necessary context to the generator model to perform the text generation. There's another preliminary called the wizard of Wikipedia dataset for dialogue generation. The setting is that there are 2 speakers speaking to each other, the wizard and the apprentice. The wizard can access to a knowledge source, such as Wikipedia in this case, while the apprentice, the student, does not have the access to the knowledge source. As for the annotation, each wizard utterance is annotated with knowledge sentence. And therefore, there are 2 tasks enabled, dialogue knowledge selection and dialogue response generation. So in this project, we are interested in multi-source open domain dialogue generation. Specifically, our research question is, how do the knowledge from multi-sources interact with each other? And what if new knowledge is added after the training is done already? So an intuitive application of multi-source dialogue generation is nowadays a coding assistant, such as GitHub Copilot and Amazon Q that I believe many of you have already used already. So in this coding assistant, there's a chat system based on the LLMs specialized to coding domain. And these chat systems has to integrate information from multiple knowledge sources, such as the user query, the user highlighted code, the current opened file, opened files from, other files from the same repository, and also the search engine return results. So back to this work, prior works either used single source knowledge for dialogue generation. For example, Wizard of Wikipedia, WoW is the case. Or alternatively, other works used post-retrieved multi-source dataset, which is unable to evaluate the knowledge selection performance. So inspired by these observations, we propose a new dataset called multi-source Wizard of Wikipedia, shortened as Miss-WoW dataset. Here's an example illustration of our Miss-WoW dataset. So we divide the knowledge in the Wizard of Wikipedia dataset into 4 non-overlapping partitions of knowledge sources. And then we replace the knowledge sentences in WoW dataset with knowledge tuples from different knowledge sources, such as OPIEC, semantic frame, and Wikidata. Meanwhile, we retain the utterance level knowledge annotation provided by Wizard of Wikipedia dataset. Therefore, as a result, Miss-WoW dataset is a multi-source dialogue dataset with utterance level knowledge annotations. So having collected Miss-WoW dataset, we use it for dialogue knowledge plug and play challenge, which aims to test an already trained dialogue model on using new support knowledge from previously unseen sources in a zero-shot fashion. Specifically, we ablate one of the knowledge source during the training and then add it back during the testing phase. So for the tasks, we fine-tune the Roberta model for knowledge selection and the BART model for the response generation. So for the interest of time, I will quickly go through the results here. So for the dialogue knowledge plug-and-play challenge, we got the following results. First, we found that dialogue generation with Go knowledge significantly outperformed using the other type of retrieved knowledge. We found that the larger the ablated training knowledge is, the worse the test performance becomes. And the selection and generation performance vary across very different knowledge sources. Most interestingly, we found that during the zero-shot adaptation phase, including more knowledge inputs improve the performance. This is actually similar to the in-context learning we see a lot today. And finally, we found that small language models and both small language models and large language models show similar trends. So overall, in this project, it shows that how the model behavior changes as we vary the inputs in a RAG-like setting. Okay, so given the foundation of CORA and the RAG, then how can we integrate the idea of RAG to relative work generation? In this project, we studied the grounding of citations with cited text span. So prior citation text generation works all use the abstract to represent the cited papers, while cited text span, shortened as CTS, it refers to the specific span in the cited paper that the Go citation refers to. And this should be the ideal solution to this problem. However, manual CTS annotation is very expensive, and the existing CTS datasets are too small for training the neural network models. So therefore, in this work, we explore 3 ways of leveraging CTS. The first way is that we train a dense passage retriever model and then use the citation context, which is just 1 or 2 sentences before the target citation as a query. This process is fully automatic. Alternatively, we try to use root score to retrieve CTS that is most similar to the Go citation text. But this is clearly cheating because during the testing, we do not know the target citation text that we want to generate for retrieving as a query to retrieve the CTS. So therefore, we propose a third approach, which is human in the loop. So given the human user proposed keywords, we use this keyword to retrieve the CTS and then use the CTS to generate the citation text. So again, I'm going to be brief here for the interest of time. More details are in the chapter 5 of my dissertation. So overall, we found that all the results that shows that the CTS is a better representation of the cited paper than the cited abstracts. We found the retrieved inputs are more supportive to the target citation text with less hallucination than the cited abstract. We found that we obtained strong citation text generation performance based on the CTS. And the CTS-based generation is really liked by the human annotators, human evaluators overall over than the abstract-based approach. And finally, we found that the predictive citation text is also closer to the inputs for the CTS compared to the cited abstracts. Okay, so far, we only showed the performance based on the distantly retrieved CTS. But how does the distantly labeled CTS compare to the human annotated CTS? So the figure on the left shows that distantly retrieved CTS have significantly good overlap with the human labeled CTS. And similarly, the figure on the right shows that this distantly retrieved CTS have significantly good overlap with the target citation text. So when the top K number is larger than 6, then distantly retrieved CTS already outperform the human annotated CTS. Moreover, under an apple-to-apple comparison, distantly labeled CTS performed similarly as the human labeled CTS on citation text generation. Because human annotation is so expensive, we claim that we can simply just use distantly labeled CTS to replace the expensive human annotation process of CTS for citation text generation. And as a conclusion in this work, we showed distantly retrieved CTS is a better alternative than the cited abstracts for citation text generation. So far, until here, we still have some unclear points about RAG. First, dialogue knowledge selector doesn't seem to be as effective as claimed in the prior works. This is a case for Miss Wald projects where we didn't find knowledge selector really helping. And it's also the case in my recent Amazon project. And the second confusion is that we found the citation text generation performance improves overall as the number of retrieved CTS increases in general. But why is the case? So motivated by these questions, we performed the next study of the relationship between knowledge quality and the RAG performance. In this RAG simulation experiment, we basically given a data set with human answers and gold knowledge that human annotated. For each example, we sample gold knowledge and distractor knowledge, and then blend them together to simulate the output of a knowledge retriever and selector. And then we study the knowledge retrieval and selection scores versus the generation scores. So we started here. We repeat this procedure for multiple times to simulate the outputs of the knowledge retriever and selector of different knowledge scores in order to answer the research question of why knowledge selectors are not as helpful as prior works really claimed before. So here are the data sets settings that we use for this experiment. For the data sets, we picked two data sets. The first one is Wizard of Wikipedia, our old friend. Again, the setting is that there are two-party dialogue based on the Wikipedia corpus. And again, there are human annotated knowledge selection and human annotated responses included. And to note that these tasks has a large solution space, meaning that human annotation may not be the only plausible answer. To complement the characteristic of Wizard of Wikipedia, we also choose another dataset called HOPO-QA. It's a question answering dataset derived from Wikipedia as well. Note that this dataset is created with gold knowledge graph injected with the distractor knowledge graph. Therefore, the answer is likely to be unique without ambiguity. As for the generator models that we use for the simulation, we use three types of generators: GPT-4o mini as a relatively stronger generator, and Llama 3.18b in the middle, and Mistral 7b instruct as a relatively weak generator model. We got a whole bunch of very interesting results. First, we found that RAG for LLM is beneficial, even though the LLM may seem, we have seen the Wikipedia articles during the training already. We consistently find that RAG with gold knowledge outperforms full knowledge setting, which is full knowledge setting means we do not use a knowledge selector and directly feed all the knowledge available to the generator model. And this full knowledge setting further outperforms the no knowledge setting, which means we only rely on the LLM's memory without any retrieval. Further, full knowledge setting without the knowledge selection is a very strong baseline. We used the same LLM as the generator for knowledge selection, but none of these LLM selectors outperforms the full knowledge setting. And we found a similar trend for the HOPO-QA dataset as well. More interestingly, we found that, so in these figures, we found the knowledge precision and recall together are good indicators of the generation performance. So in the figures, x-axis and y-axis represent the knowledge precision and knowledge recall score, respectively. And we found a smooth transition of the colors as we vary the knowledge precision and the recall scores. These colors encode the RAG generation performance. And we use the orange color to indicate the color, to indicate those data points whose RAG performance outperforming the full knowledge setting. And the cyan color here indicates the performance underperforming the no knowledge setting. So as a reminder, RAG in general involves document retrieval, knowledge selection, and final response generation steps. While the knowledge selector step can only improve the knowledge precision score, but this is unlikely to. But meanwhile, I mean, it's also likely to reduce the knowledge recall score naturally. So reflecting in these figures, it means we start with the upper left corner, for example here, and then moving towards the lower right corner. So like maybe here, if we improve the knowledge selector. And if the knowledge selector is perfect, if we apply a perfect knowledge selector, then maybe we start from here and we directly move horizontally to the right, to rightward, to like maybe here. So our next observation is that knowledge recall is the most crucial knowledge metric for strong generators. Taking the GPT-4o mini on Hopper QA as an example, this trend is very obvious. So knowledge recall, this one is very clear to see the trend. And further, so these figures are the color contours of the RAG generation answer F1 versus the knowledge precision. So F1, generation F1 and versus the knowledge precision scores. Each contour represents a different knowledge recall score. And moving from left to right visualizes improving the precision score of the knowledge selector. We found that knowledge capacity, we found that the generator model's capacity determines both the overall performance and the usefulness of the knowledge selection. Specifically, the generator capacity determines the benchmark scores. So given a stronger model, all the three generation scores with gold, knowledge, full knowledge, and no knowledge are higher. This is very intuitive. So see the number, it's 0.8, then 0.55, then like 0.3. Moreover, the generator capacity also determines the room of improvement by the knowledge selector. So given a strong generator model, the room of improvement from the full knowledge setting, so in red dashed line, to the upper bound of the performance, which is the goal knowledge setting, is narrower. So here the range is narrower and wider and even wider. Again, so the full knowledge setting means that we do not use a selector model. Moreover, we found that the task and data set are also key factors in the RAG performance. As we explained before, Wizard of Wikipedia dataset is noisy, while Hopper QA dataset is clean dataset. And looking at these two examples, the Mistral 7B model on Hopper QA behaves very, very differently from all other models or other results. Our last point of observation is that we find a non-monotonic trend in the improving of knowledge selector for Wizard of Wikipedia dataset. I also find a similar trend in my internal Amazon's project as well. So in these Wizard of Wikipedia figures, there's a clear dent in the orange area. So a dent, a concave dent, dent, and a dent. This means when we improve the knowledge selector by moving lower right, then the generation performance may decrease first. So from lower to a lower right direction. So from, for example, from here to here, then the generation performance may decrease first and then increase later as we improve the knowledge selector. And we only observe this trend in Wizard of Wikipedia dataset because it's relatively noisy. That means low precision and recall metrics measured here doesn't necessarily truly mean that the retrieval result is bad. And we have more experiments and details in the chapter 6 of my dissertation to explain this phenomenon. So as a conclusion of this simulation experiment, we found the duality of RAG. That is, a strong generator model is robust to noise. Therefore, it prefers more retrieved gold knowledge despite the presence of distractor knowledge. And a weak generator model, on the other hand, cannot handle distractor knowledge and requires a selector to refine the noisy input knowledge. Note that the strength of the generator model is relative to the task and dataset because we can artificially create a very hard dataset that makes even the SOTA LM behave like a weak generator model. So as a conclusion, we have some recommendations to the future practitioners for this type of experiment. First, pick a strong generator model and then benchmark no knowledge setting, full knowledge setting, and gold knowledge settings. And then prioritize improving the knowledge recall score by improving the knowledge retriever. And finally, only when the knowledge recall score is high enough can a knowledge selector be potentially helpful. Otherwise, even a perfect knowledge selector cannot help at all. So in contrast to the classic setting of the retrieval augment generation, where we always encourage the retrieve the relevant information as much as possible to improve the generation performance. In this work, we study a pretty different KINOG setting as before. So in most of the prior KINOG tasks, they assume sparse gold knowledge. But what if there are too much redundant relevant information? So, and actually this case is very commonly seen. For example, in claim verification, which refers to the task of checking whether the claim is supported or not based on the retrieved evidence. Or in our previous CTS project, we observed retrieving a lot of semantically redundant CTS. So based on these background, we propose a new concept called minimal evidence group that fully supports the claim and with non-redundant evidence as a member of the evidence groups. And the size of the evidence group is minimal. So as a background and related work to, so the classic claim verification tasks usually consists of 3 steps: evidence retrieval, evidence selection, and stance prediction. This is, in fact, an inverse of KNLNG, which given the generation output, and then it matches the inputs. Our proposed MEG identification extends the step of extend the steps in classic claim verification on the evidence selection and stance prediction steps. Note that none of the prior works address the redundancy problem within an evidence group. And more importantly, so it is insufficient to simply break the claims into subclaims. Even an atomic subclaim can have partially supporting evidence pieces. Taking a concrete example, person A did not violate any law. To really support this claim, then we have to enumerate every law statement, but each of the statement is only a partial supporting evidence. So in terms of the modeling, previous works all worked on the predicting the single pair of claim and the single evidence. But this setting is problematic when there are partial evidence or there are multiple sets of supporting evidence. To formally define MEG that we propose, we define a claim verification task taking a claim and a list of candidate evidence pieces or sentences as the input. The evidence selection step retrieves all evidence pieces that are relevant to claim, and the stance prediction step predicts whether the selected evidence piece supports claim. We define a set of fully supporting evidence pieces as evidence group. And finally, our minimal evidence group means it's fully supporting the claim. So partially support is insufficient. And the member of the evidence group should be non-redundant in terms of supporting the claim. And finally, the number of the evidence pieces in the evidence group should be minimal. To motivate our approach, first, there's no prior data set nor model available for MEG identification. And we also found that directly prompting the LLMs show poor performance. And further, we can prove that this problem is NP hard. So therefore, we have a cold start problem. And for our proposed approach, we propose an exact solution by taking the bottom-up approach to decompose MEG identification into base problems. We iteratively perform the base problem of classic claim verification and then aggregate the result back to obtain the MEG. The base problem specifically here means predicting whether a candidate set of EPs fully supports, partially supports, or does not support the claim. And note that our proposed approach is an aggregation of the classic claim verification. Therefore, the base case of our approach is identical to the classic claim verification. And this is very different from simply just training a model for direct prediction of MEG. So here's our proposed algorithm. We do a bottom-up brute force approach to iteratively merge partial supporting evidence until we find the MEG. The base model here can be implemented with any reasonable approach, such as prompting LLMs or fine-tuning small language models like P5 model. So therefore, a strong base model of classic claim verification results in a good result in the MEG identification. Again, there are no appropriate prior data sets for our experiment. Therefore, we had to filter and convert classic claim verification dataset to align our MEG identification task. For each of the example and for both of datasets, we have annotations of multiple evidence groups. And we assume the annotated evidence groups by human are already minimal because humans are actually good at it. And in addition, all the claims we use are already atomic claims. We use two datasets, SciFact and WISE. SciFact is a biomedical claim verification, and WISE is a claim verification dataset based on Wikipedia. For the settings, we consider the following three baselines. Direct prediction using the LLM with zero-shot prompting and classic claim verification. So this is, again, a base case of our approach, which simply takes all the evidence pieces as a single evidence group. in addition to this classic claim verification, we apply removal of pairwise redundancy as a third baseline. And for the evaluation, we measure the metric of exact match and the best soft match, which gives some partial credit to the prediction. And we prioritize precision at 1 score. So here are the results of our MEG identification. Our proposed approach performs the best, while the directly prompting the LLM performs the worst. And we also found that applying redundancy reduction helps improving the performance over the classic claim verification setting. Next, we want to show the helpfulness of MEG as a compact set of RAG retrieval result that is particularly suitable for low computational budget setting, such as on-device computing. So our example task is the inverse task of MEG called budgeted claim reconstruction, another type of KI-NLG task. The setting is that we consider our previously obtained MEG, and also we compare the union of evidence groups and the first K truncated evidence pieces. Given these results, we found that MEGs are much more compact with more than 45% fewer words achieving similar generation performance. So here are some important discussions. When there's no MEG found, then practically we can still obtain the union of the partial supporting evidence as a byproduct. And the next point is that due to the NP hardness of MEG identification, our exact solution trades off the running time for higher performance. That means given a perfect base model, our MEG identification performance should be also perfect. And there's also a faster approach to compute MEG, such as the classic setting with lower redundancy that we presented before, but this is less accurate. And for the future work, currently our proposed approach is more suitable for high quality dataset annotation, which requires robust solution without strict running time requirements. And future works can use our exact solution proposed to create a larger scale dataset and then train a well-performing fast model on that dataset. So essentially the idea is similar to distilling system 2 into system 1, which is essentially distilling logical reasoning into simple reflex. So our last part of the work is about harnessing the LLMs for domain-specific tasks, such as we take the section-level full relative word generation as an example. So as a background, the previous extractive relative word generation extracted salient sentences from the cited papers and concatenated them all together as an output of the relative work section. So there's no transition sentences considered at all. While previous abstractive relative word generation works, they worked on generating individual citation texts before LLM came out. So as a result, both prior extractive and abstractive relative word generation approaches, they all ignore the relationship among the cited cited papers in the relative work section. So in this work, we study how to generate the relative work section with a coherent story. We use stepwise generation by first generate these features using the GPT 3.5 turbo model, and then gather all the features we generated and use the GPT-4 model to generate the full relative work section. Due to the challenging nature of relative word generation evaluation, no model nor ordinary person can really evaluate relative work section. Therefore, we asked 27 experts who are either the authors of the relative work sections or very familiar with the target paper for the human evaluation. We ablated various features and then scored human evaluation metrics in 5-point Likert scales. So we got a whole bunch of interesting results. As table 4 shows, we found most of the features we propose useful. They are the main idea of the target related work section provided by the user, human user, and also the target paper's title, abstract, introduction, and conclusion section. And the third is the citation intent or relationships between each cited papers, and also the cited papers abstract. And finally, sometimes cited text plans are also very useful. More interestingly, we also used the COA joint related work tagger that we introduced previously to predict the citation types of each generated citation for writing style analysis. So as you can see in the red boxes, both related work section contain much more reference style citations than our generated related work sections. This indicates our generated related work sections are more like the concatenation of the summary of each cited paper, while the human written related work sections tend to use coherent story to connect short citation spans together. More interestingly, we found that there's a strong correlation between the human preference and the Rouge L scores, and also between the Rouge scores and the proportion of the reference type citations shown here. By the way, so the Rouge score, measures the similarity between the output related work section and the gold related work sections. So overall, this observation implies that the readers prefer more high-level abstract citations with transition sentences between them to provide a coherent story. So finally, we summarize the challenges we identified in related work generation. First, we found that the factual errors are something that human readers are very sensitive to. And we didn't talk about this in detail, but please refer to my chapter 8 dissertation for more details. The next challenge is citation ordering and organization. So this is mostly underlooked by most of the prior works. In our work, we found that the human readers do not like simple concatenation of the cited paper summaries. And it's important to emphasize the right cited papers, not the random ones. And as a future work, we suggest automatic citation ordering and grouping. The third challenge is the transition sentences and the writing style. So previous extractive related word generation and citation text generation did not really consider this at all. So we suggest distinction between the reference type and the dominant type citations. Our final challenge is retrieval augmented related word generation. So far, all existing related work generation works all assume the list of cited papers is available already as an input for this task, which is clearly unrealistic. So as a future work, we suggest start with a partial list of works that should definitely be cited, and then iteratively, and then alongside a set of also alongside a set of candidate works that might be related, and then we iteratively use retrieval augmented generation to select a candidate paper and then generate its transition and citation sentences. So in this last slide, I will summarize my overall topics for the KIMOG dissertation. So for the related word generation, which is a task-specific challenge, we studied finding appropriate unit of generation for the core project and selecting specific input knowledge from very long cited papers for the cited text span project, and modeling relationships among cited papers for the related work food section related work generation project. And for the general challenges for the established tasks, we also studied adapting to new knowledge sources in the MIS-WOW project and balancing knowledge quality and quantity for the MEG identification project and the RAG simulation project. And finally, harnessing the LLM generation with generation plans in the Wizard of Shopping project, which I skipped. And please refer to chapter 9 of my dissertation. That's it. Thank you. Thank you everyone for attending my defense, and really appreciate everyone's help here. Thank you.